All right, so we're going to check out the midterm questions right here. So first one, number one, we had to find the limit as x approaches 6, and we want that to equal 8. So the first thing to do is get rid of anything that doesn't actually approach 6. So all of these are negatives, so we don't want to pick those. These ones do approach 6, so that's okay. These ones also approach 6, that's okay. These ones we have no information about 6, and these ones we also have no information about 6. So we really just want to pick between one of these two options. We want this to equal 8, so we would have to see which one best fits 8. Of the two, this one right here is going to be probably the best choice. So I'm going to go with B. That one would best reflect the values. All right. For number 2. So this one's pretty difficult. This was the hardest one on the test. And a lot of people got tricked. So this one says f of x is sine of 2x. Find d dx of the inverse. So a lot of people just said, well, I got sine, so the inverse of sine is arc sine, but that's not the case because our function y equals sine of 2x. If we were to take the inverse of this, we would have x equals sine of 2y, which means we'd have arc sine of x equals 2y, or 1/2 arc sine of x equals y. So we can see that we just have the x inside of the arc sine. The 2 actually is going to be outside. So we'll get 1 minus x squared for the derivative, because we will still use the arc sine rule. And it actually ends up being b over here. So a lot of people picked C. A lot of people wanted to put the 2x inside. But the 2x actually is not inside. This one's pretty tricky. So the person that wrote this, they made a pretty tricky question. That was a pretty interesting one. All right. Number 3, this was a really good question according to the program, because people that did well on the test generally got this one right. People that did not do well on the test generally got this one wrong. So it's a good one to see, all right, if I understand this one, I'm probably in a pretty good situation. So we have to find the derivative of negative tangent of 15x cubed. So this is a chain rule question. So in this case, we want u to be 15x cubed, because that's the inner function. The outer function y is going to be negative tangent of u. So derivative of tangent is secant squared. The negative sign just hangs out front. It's like multiplying by -1, so that's the constant multiple rule. But du is going to be 45x squared for the power rule. So 3 times 15 is 45. So when we put it together, we'll get 45x squared times negative secant squared of u. So that means we're going to get negative 45x squared times secant squared, and then u is 15x cubed. So this one is going to be B. So that's what we get for that one. All right. For number 4, we have to find the average rate of change. So the average rate of change formula, that's our f of b minus f of a over b minus a. We have our interval 1 to 5, so this is going to be a, that's going to be b. So what we want to do is just look all this information up in the table that we're given. So f of b is going to be 14, because b is 5. To get a is 1, so f of a is going to be 2. Oops, wrong place. We want f of a first. And a is going to be 1. So when we simplify this, we get 12 is 14 minus 2. 5 minus 1 is 4. 12 divided by 4 is 3. So we end up with 3 there. So 5, which of the following must be true of function f of x is not continuous at c? So I thought this was interesting because, again, we usually deal with continuous functions, but this person wanted to look at things that were not continuous. So the first one says the function is defined at x equals c. And that doesn't necessarily have to be true. Again, we can make a function like this that's not continuous, and I guess that would be defined. So let's go ahead and get rid of this. So this is not defined at x equals c. However, the limit does exist. It is not continuous. So we don't have to make sure that we're defined at x equals c. Next one says that the limit of f of x does not exist at x equals c. Now for this one might happen. So number 2 doesn't really follow a must. So if the limit of f of x does not exist at x equals c, it's not a given necessarily that we are not continuous at x equals c. It's usually the case, but we see some of those infinite limits where the limit actually is infinity. We would say the limit's infinity at x equals c. So in that case, it's not continuous, but the limit is an infinite limit. That leaves part C. If the limit exists and it's not equal to f of c, then you know you are not continuous. So in this case, we're going to go with B. Again, this one was pretty tricky. A little tricky symbol out there. For number 6, it says a particle moves along the x-axis at time t is greater than 0. So we've got the position. At what times is the particle at rest? So I thought this one was pretty fun. We've seen things like this before where the goal here is if the particle is at rest, that means that the velocity has to be 0. So what we need to do is we need to take the derivative of position, and they did x of t instead of s of t, but that's okay. They told you it was position, so they gave you the heads up. But we need to go ahead and take the derivative of this one. So this is going to be v of t. So this is going to be 6t squared by the power rule minus 42t by the power rule again, plus 72 by the power rule, and then 53 is a constant, so its derivative would be 0. Now, again, since we want to be at rest, we need to set this equal to 0. So 0 equals 6t squared minus 42t plus 72. And this was pretty creative. They actually made you divide everything by 6 in order to solve this somewhat efficiently by hand. Again, you could do it without dividing everything by 6, but I like that they put this in here. That was a pretty interesting idea. So we got 72 divided by 6 is going to be 12. Because now we can factor this. This will factor into t minus 3, t minus 4. So we know that t equals 3 and t equals 4 in order for this to be true. So we can go ahead and pick E, and E is the right choice on this one. So very nice job. This one was pretty creative. I like that one. For number 7, not too many people make questions like this, which is why I thought this one was an interesting one. We have to get the meaning of the derivative over here. So it says h is a differentiable function of t that gives the temperature in degrees Celsius. So I know that h is measured in degrees Celsius at the Arctic weather station. Which of the following is the best interpretation of h prime of 24? So this is going to be in degrees Celsius at a time. So we want to find the rate of our degrees that are changing at a time. Well, that does not have the correct units. This is just a temperature, so that's out. This is a temperature, so that's out. The drop in temperature might be a choice. The rate at which the temperature is changing would also be a choice. So these are both ones that we could pick. However, we don't know if we're actually dropping. We just have h prime of 24, so we have to pick E. This has to be the rate at which the temperature is changing at the end of the 24th hour. Not the overall drop in temperature. Again, depends on the way that you would read the word drop. So if you write it as a rate of change, you don't know if it's going down or up, so you can't pick that one. If you write it as a delta T, again, we're not going over time. It just says at that hour, so we want to pick E. All right, for number 8, we have to pick which one has the removable discontinuity. So a removable discontinuity, again, if we think about this in terms of graphs, this is going to be where the holes are at. This one has a hole at 3, so we're going to probably pick that one. There's no hole here. This would be not differentiable, but it is continuous, so it's not a discontinuity. This one's a jump discontinuity, so it's not removable. This one's an asymptote. You can't remove that. And this one at 3 would just be 21 over 3 or 7. That's just continuous, so we don't want to pick that one. For number 9, everyone got this one right, so it's got nice little easy blocks over here. Derivative of 4 ln of x. 4 is constant multiple rule. Derivative of ln is 1 over x. So we get 4 over x. All right. For number 10, we have to find this limit, and there's a couple ways to do it. You could do it like unit 1 and just pick 1/6. If you did it with L'Hopital, you could check sine of 0 is 0. 6 times 0 is 0, so you do get 0 over 0. So we get to take the derivative of each of them. Derivative of sine is cosine. Derivative of 6x is 6. This is the limit still as x approaches 0. And so when we plug that in, we'll get 1 over 6, because cosine of 0 is 1. Let me actually write that out. That might be a little bit too fast. There we go. All right, sounds good. For number 11, everyone got this one as well, so that's pretty nice. That's good we remembered what the derivative of a constant was. No one got thrown off by the 5. Derivative of the constant is 0. Any of that's flat, so no rate of change. So nice job with that one. For 12, this one's also got a nice ribbon here, because this was a good one that differentiated between people that scored well and people that didn't score well. So again, if you know this one, or if you missed this one, this would be a good one to study, because it's showing that, hey, a lot of people that did well on the test got this one right. So when it comes time for the AP test, if you can get this one right too, then you'll be right up there with some of the high scorers. So we have to find the limit as x approaches 2 of f of x. So again, when we're talking about the limit, we want to see what it approaches. We don't really care about the actual value. So we need to find out what both sides are headed towards. And in both cases, we're headed towards the number 2. So since both sides are headed towards 2, we're going to pick 2. For 13, P of t is the size of the population times t, which describes linear growth in the size of the population. I think remember we went over this one, a similar question like this as a homework question. We said that to have linear growth, we need to make sure that our slope is just a number, because remember, derivative is kind of the same as slope. So if the slope is 200, that's going to be a graph of a line. All these other ones are not going to be lines. They'll all be curves. So we got to pick number 13, because again, this 200 is constant. All right, for 14, let f be a function of x, which the following statements, if true, would guarantee there's a number c in the interval 0 to 4, such that f of c is 15. So this really feels like it's all about the intermediate value theorem, so we need to make sure we satisfy the intermediate value theorem. So we have an interval, we have a closed interval, which is good. The other thing that we need for the intermediate value theorem is we need to be continuous. So we're going to get rid of these 3 because they don't say continuous. Since we want 15, we want to see what 15 would be between. 0 and 20 would be okay. Between 20 and 30 would not be okay, because 15 is not between those. So we're going to pick B for that one. So I like that one too. That's a pretty interesting way to ask about the intermediate value theorem. So I like that one that the author made for this one. For 15, find the limit as x approaches infinity of ln of x over x analytically. This is just a really fun one to do with L'Hopital, because when we plug in infinity, we do get infinity over infinity. So it's nice that we don't get a 0 over 0. It's good we get something a little bit different. So we are going to L'Hopital this one. The derivative of ln of x is 1 over x, and the derivative of x is 1. So this is pretty fun. We're taking the limit as x goes to infinity. So this is going to be 1 over x, but the limit of a number over infinity is 0. So that one turns out to be 0. I like that one. That one was pretty cool. I thought that one was fun how it worked out. So the author for that one made a pretty fun L'Hopital question. All right, number 16 was pretty tough. And yeah, I thought this one was kind of tough when I read it, when I saw what the person who made this question was going for. I wasn't quite sure how many people would notice this one. And that's because we have to actually use this xy equals 18 as part of our rate box. This is a related rates question, so we are going to do a little bit of dreads. So we've got our particle, and it's moving on a hyperbola, such that x times y equals 18. We're at y equals 6, so that means x is going to have to be kind of up here. It's wrong place. Here at 3. We got 3, 6. And the reason for that is because 3 times 6 would be 18. So that was kind of the tricky part about this one, was making sure that you figured out what x was. So I thought that was a creative way. Wasn't sure how many people were going to pick up on it, but it's a good one to have on a test because it's an interesting one to see how it's actually done. So with the rate box, yeah, we had y equals 6. We can figure out that x is 3 because we know xy equals 18. So we can figure that out by dividing both sides by 6. Dy dt is 8, and then dx dt is going to be our question mark because this is asking how x is changing. So our equation, they give us the equation, which is also pretty nice. So xy equals 18. And this is the other thing that was interesting about this one is this is just a product rule. So you can't just do a power rule or anything like that. So this is going to be x dy dt plus y dx dt equals 0. I thought that was really cool when I did this one, just because of the way that you have to actually write everything out from the product rule. So it really tests the product rule as well. So there's a lot of nice, fun moving parts in this one. Substitute and solve at this point. That would be our derivative. So, yep, we know x is 3. We know dy dt is 8. We know y is 6. We don't know dx dt, but that's okay because that's what we're trying to figure out. And then we got to solve this. So let's just divide everything by 6. So 3 times 8 divided by 6 would be 4. 4 plus dx dt equals 0. We could subtract 4 from both sides. So we get dx dt equals negative 4. So we know we're going down by 4 units per second. I thought that was a really cool question. So that was an interesting way to ask one of these dreads questions, using a more of an analytic approach rather than all those real world interpretations that we had. But this is how we started out, right? Because we started out by just looking at some of our particles and just some of our equations and working with those and building up to some of our more complex situations. So that was pretty cool. I thought that one was interesting. Again, it was a little bit difficult, but definitely appropriate for the test. All right, for number 17, let g be a function given by g of x is the absolute value of x, which of the following is true. G of x is differentiable at 0. That's not true because here the slopes are different. So that one's out. G is continuous at 0. That is true because both as the limit as you approach from the left and the right are 0. So that's fair. G of 1 exists. We can plug 1 into the absolute value and get an answer out. So the answer is going to be 2 and 3. All right. For 18, everyone got this one, which was pretty nice. There's a lot of different strategies you could do to do this one pretty quickly. Based on what I've got here, I'm going to look at the leading term and see if I end up with this 1080. If I do, I'm going to pick that one. If I don't, at least I can just count the number of terms I'd have left, and I'd answer with one of the other choices. So if I do 4 derivatives of this, so I start with y equals 3x to the 6th. So y prime is going to be 3 times 6, x to the 5th. Y double prime is going to be 3 times 6 times 5, x to the 4th. Y triple prime is going to be 3 times 6 times 5 times 4, x to the 3rd. And then y to the 4th, so fourth derivative is going to be 3 times 6 times 5 times 4 times 3 times x squared. Now again, you might think, well, that's pretty weird. Why did you not actually do any of that multiplication? Again, I want to try and do multiplication the fastest or the easiest way it is for me. So if I'm multiplying as I keep going, my numbers are just going to get bigger and bigger and bigger. Whereas if I do it this way, now I can see, oh, okay, this is 30 times 9, which is 270 times 4, x squared. And at that point, it's like, yeah, 270 times 4 is not going to be any of these choices. So we got to go with 1080. And that's the end for that one. So I didn't actually do all of the derivatives for all of the terms. That was the one I chose to do. Like I said, there's a couple different strategies you could do to do this one quickly. You could also cancel out all these terms that are not to the 4th power or higher and follow the last term because this person designed the question pretty well so that all the last terms were different. So that would have been a good strategy as well. The only reason I didn't pick that is I felt the 3 was going to be easier than the 8. I don't know if that's the best choice. Probably not because we got 192. So you could also go ahead and do it that way. All right. All right, so this is number 19 then. So again, this was one of the trickier ones. So we're taking the limit as h approaches 0 of cotangent 1 minus h minus cotangent of 1 over h. So this was back when we did our limit definition of the derivative to show that this is actually just asking for the derivative. So this one wants you to take the derivative of cotangent of x at x equals, not 0, 1. I put a 0 there. So what we're going to do is we're going to take the derivative of cotangent. So the derivative of cotangent, but we already know that one now, is going to be negative cosecant cotangent. And what we're going to do is we're going to plug 1 in for x. So negative CSC of x, negative cosecant of x is going to become negative cosecant of 1. And then cotangent of x is going to become cotangent of 1. And so we're going to end up at c. So that's what we want to do for that one. So again, we just have to remember that this, when our derivatives look like this, they are derivatives. So this limit is actually a derivative in disguise, and we need to be able to translate between the two different function or forms of the function. All right. So then for number 20, when it loads up. There we go. So 20 says, Joe dropped a rock in a pond. The rock sends a circular ripple with a radius of 3 centimeters. The radius is growing at a rate of 1 centimeter per second. At what rate is the area growing? So again, we've got a nice little dreads question here. This one's, we've got our picture. Our ripple is going to be 3 centimeters and somewhat circular. So let's get our right box going. We know that the radius is 3 centimeters. We know that it's growing, so dr dt is going to be 1 centimeter per second. And it says at what rate is the area growing? So we know we need dA dt. That's going to be our question mark in this question. We need an equation. So since we're dealing with area of a circle, we're probably going to use the area of a circle formula, a equals pi r squared. We can take our derivative, so dA dt is equal to 2 pi r dr dt. And then we just have to fill in. So dA dt is what we're trying to find. 2 is going to stay as 2. Pi is going to stay as 2 as pi. The radius is going to be 3. And then dr dt in this case is going to be 1. So in this case, we'll end up at 6 pi. And since we're doing an area, we're going to do centimeters squared per second. All right, and there we are. Where is that at? That is choice E. There we go. So we got E. So pretty cool one. So nice dreads question. So number 20 is a good one. For 21, this one I thought was pretty interesting because it looks like there might be some tricks to do here, but you really can't. You really just have to go ahead and just go all out with the quotient rule. So that's the plan, is to use the quotient rule. So to do the quotient rule, we're going to do low d high minus high, so x plus 1, d low, x squared plus 1, square the bottom, and away we go. So this looks like it's pretty good. It looks like we're headed towards either A or D because it's got that x squared plus 1 quantity squared on the bottom. But we do need to be careful just in case that's going to cancel out with something on top. We do need to simplify the numerator just to see in case it does cancel out with anything. So this is pretty nice. 1 times x squared is x squared. 1 times 1 is 1. Over on the other side, we get x squared times x is minus, oh wait, hang on, that's high d low. Wait a second here. That's a little too much up there. There we go. So the derivative of low would be 2x. All right, so now let's distribute this 2x. Okay, so 2x times x would be 2x squared, and then 2x times 1 would be minus 2x. Not going too well today. All right, There we go. Again, the denominator is still x squared plus 1 quantity squared. But when we try and simplify, the only thing we can simplify is negative 2x squared minus x squared is negative x squared. In standard form, minus 2x would come next. And then we get plus 1. And then we have over x squared plus 1 quantity squared. So at this point, we're kind of done. We've actually picked out choice A. This is next to the third power, so we don't want to pick that one. That's it. So a nice little quotient rule. Pretty good. So I like that one. The derivatives aren't too crazy to do, but you still get a lot of practice in with the quotient rule. All right, for 22, this one was also one that if you missed it, might be a good one to check out because a lot of people who scored well did get it correct. Which of the following statements must be true? F is a continuous function such that f of 1 equals 3. So since we know that f of 1 equals 3 and we know it's continuous, that means that we also know that the limit as x approaches 1 of f of x is equal to 3. So we need to connect these two pieces together in order to answer the question. So the limit as x approaches 1 of f of 2 of x, well, if we put 1 in here, this would be f of 2. We have no information. If we put 1 in here, we'd get f of 2. We have no information. If we put 1 in here, we'd get f of 1, but we know what f of 1 is. F of 1 is going to be 3 if we take that limit. So that's out. F of x quantity squared, well, we know what the limit if x approaches 1 of f of x is. It's 3. 3 squared is not 3. 3 squared is 9. So we end up at e. So this is going to be those limits. But we have to use all those limit properties from like all the way back from near the beginning of the class. So pretty cool question. I like that one. That was pretty nice. For 23, this was the other one that I made. So the function is graphed for what value f of x does the derivative equal 0. So this is about estimating what our derivatives are from a graph. If we test out all the options, A says we're at about negative 3, 1, 2, 3, a little bit before. We can tell that that line is not flat. That does not have a slope of 0. Negative 1.5 would be right here. Again, we could tell that that line that's tangent would not be flat, does not have a slope of 0. At 0 itself would be right here. We can tell that, again, that line does not have a slope of 0, so the derivative would not be 0. X equals 2 would be right here. Even though that's a 0 of the function, the derivative of the tangent line is not 0. Then we get 1, 2, 3 in a little bit. So that would be right here. And yeah, that's where our tangent line actually does end up being 0. So that was the goal for that one. That was the section that came from, was when we did our estimating the derivative of the graph and choosing the best estimate. So there we go. For 24, 24 ended up being kind of tricky. And I can see why. This person put in a really subtle thing. We have to find the slope of the line tangent to the curve at a given point. However, when we do the derivative here, derivative of x squared is 2x. Derivative of 4y is 4 dy dx. And that's all pretty normal. But then they snuck in this 2xy, which is a product rule. So we have to do plus 2x dy dx, and then plus 2y. Derivative of 8 is 0, so that's just going to be 0. So this product rule is very sneaky. So you have to be really careful and pay attention that that one is a product rule right there. So then we're going to solve kind of like how we would normally solve these ones. We'll move the 2x and the 2y over to the other side. So we get 4 dy dx plus 2x dy dx equals negative 2x minus 2y. We'll GCF out this dy dx. So we get 4 plus 2y equals negative 2x minus 2y. Divide both sides by 4 plus 2y. And then we have to substitute in because now we actually know what x and y are here. We're given 2 is x and 0.5 is y. So negative 2 times 2 minus 2 times 0.5 over 4 plus 2 times 2. So that's going to be negative 5 over 8. So we end up at A. So A is the right choice for that one. So pretty tricky, but again, that's a pretty fair one. We've done some of these implicits with the product rule as well. That this person wanted to do one like that. I thought that was a good choice. Fun to do all the implicits, and then yeah, a little bit sneaky, but you gotta pay attention. You gotta stay on your toes for those. All right. 25. This is another one where if you missed it, it'd be good to check this one out because a lot of people who scored well did get it correct. So we have got 6 divided by x to the third power. So to take this derivative, you could use the quotient rule. I did see some people using the quotient rule on it, but it's probably going to be a lot faster if we rewrite this as 6 times x to the negative third power. So that's going to be negative 18 times x to the negative fourth power. So we have to go ahead and subtract 1 from 3 because we're using the power rule. So that's negative 18 over x to the fourth. So we end up at choice C. And that's it. That one's done at that point. So it's a quick one, but there's a lot of places where you could make some mistakes, especially if you go the longer route with the quotient rule. For 26, we need to find this limit. I thought this one was pretty interesting as well. I'm not sure exactly why this person wrote this question. They might have been anticipating it to be a L'Hopital question, which you can totally do it with a L'Hopital. But this is the reason I picked this one out, is it's pretty fun because square root of x minus 6 times the square root of x plus 6 is x minus 36. That's an a squared minus b squared, where a is the square root of x and b is 36. So instead of using L'Hopital, this one actually is a factor cancel if you want to do it this way. So then when we plug 36 in there, square root of 36 plus 6 is 12. So this one we don't actually, the intention might have been to do a L'Hopital with it. But I mean, we could L'Hopital it. Derivative of the top's not bad. Derivative of the bottom, we got that square root of x. So you have to deal with the square root. I think factor cancel is going to be faster on this one. And it's pretty cool because not everyone's going to be able to see that factor cancel, but it is an a squared minus b squared. So you can use factor cancel if you want on this one. So good design. I like there were a couple ways to do this one. Pretty fun question. 27. H is the inverse of f. We're given what f of 3 is. We have to find h prime of 15 given a function for f. So this one, very nice. It's a good inverse choice, inverse question. So h prime of x is equal to 1 over f prime at h of x. The one thing I liked about this is they didn't use g, they decided to use h instead, which is good. It's good to use some of the different letters, not the ones that we're used to. So h prime of 15 is what we're trying to find out. So we need 1 over f prime of h of 15. So you might think, all right, well, this seems like it's going to be tricky because I need to actually get the inverse of this one. But the person who wrote this told us that f of 3 equals 15, which means that h of 15 has to equal 3. So that was a good idea. So h prime of 15 is 1 over f prime at 3. All right, so they still made us take the derivative, though. We still don't know f prime of 3 right away. We have to actually do this one. So f prime of x is going to be, well, the derivative of 8 is 0. Derivative of minus 3x is minus 3. Derivative of 6x squared is 12x. So when we plug in 3, when we find f prime of 3, we're going to get 33. So if we replace f of 3 with f prime of 3 with 33, we end up at choice A. So that was pretty cool. I like that one because they did a little bit of both approaches. So in class, we saw 2 approaches. Usually they'll give us all the numbers and we plug them in, or they give us the function and we have to get the inverse and then plug it in. So I like this one. It was a mix of both approaches. So cool question. For 28, again, this is another one to look out for. We had y is x squared minus 4x, and we're given dx dt x, and we need to find dy dt. So our plan here is this is an implicit. You can do it like a dreads question if you want. But with this one, if we do it as an implicit, dy dt is equal to 2x dx dt minus 4 dx dt. We don't really need to draw everything out. We don't really need the rate box because everything's kind of right there in the question. It says find dy dt, and this is the other nice thing is dy dt is already by itself. X is going to be 2. Dx dt is going to be 3. So dx dt is 3, and we can see that we get 12 minus 12 is 0. So I thought that was a pretty fun one. Again, I like that they made it so that it equaled 0. That was pretty interesting because it doesn't look like it's going to be 0, but dy dt in this case is constant at x equals 2. Kind of cool. So good job on that one too. For 29, find dy dx given the following equation. So we got a big one, and so this is another big implicit that we're going to have to do. So we just have to be really careful with the implicit. And again, they snuck in that product rule. So we had 2 that were kind of similar on the test. This one was going to be kind of a little bit trickier than the other one just because of all the exponents this person used. But I like this one too. So it was an interesting one to have on the test. Taking the derivatives, we get 8x cubed minus 3x. So first times the derivative of the second. So 3y squared dy dx plus the second times the derivative of the first. So y cubed times negative 3. And then we've got y to the fourth. So that's going to be 4y cubed dy dx. And again, when we take that derivative of the last piece, we're going to get 0. All right, cool. So let's start moving things over. We want to do minus 8x cubed, and we're going to do plus 3y cubed. So minus 8x cubed plus 3y cubed. And this person, when they wrote the question, they wanted the x's to go first. So I said, all right, that seems okay. So all the x's are going to go first in this case, which is going to be a little odd with the signs, but that's all right. So we got negative 9xy squared dy dx plus 4y cubed dy dx equals negative 8x cubed plus 3y cubed. Now again, if we're looking at this point, we kind of already know which one we're probably going to pick. We're headed towards D at this point because it's the only one that has negative 8x cubed plus 3y cubed as the denominator. But again, we want to finish it up just in case something's going to cancel. I don't really see much hope for anything canceling here, but we'll still try it out. Why did my pen not show up? Pen. All right. So we factor out the dy dx again. Negative 9xy squared plus 4y cubed equals negative 8x cubed plus 3y cubed. Divide both sides by negative 9xy squared plus 4y cubed. Negative 9xy squared plus 4y cubed. And we hit exactly D. So yeah, it did end up being D. So pretty cool. So this one doesn't have any substitutions. You don't have to plug anything in. Just some implicits. All right, number 30, also a little bit tricky. Irrational functions are shown. Determine for which functions a graph of that function would have a horizontal asymptote. So a little bit tough because this is some stuff that you probably did in pre-calc. We did talk very briefly about it when we did our limits at infinity. So I thought this was interesting that this is what this person decided to write the question on. But, it's fair. We did our limits at infinity, so we could think about it as taking each of these. We want to take the limit as x approaches infinity for each one of these functions. So if we do the limit as x approaches infinity for this one, we're going to end up at 1/2. That's fair. There's a lot of ways to do this one. You could double L'Hopital this one. You could use the trick, which I did from unit 1, which says x squared is the biggest. That's what I'm going to look at. And then I'm going to cancel to get to 1/2. For number 2, if we take the limit as x goes to infinity, if we use our same trick, I'm just going to look at the biggest powers of x. And then when I cancel, this is going to become a 2. So I'm going to end up with 1 over x squared, which if I take that to infinity is going to give me 0. So I do have a horizontal asymptote. A little strange, but it is at 0. 0 is a valid horizontal asymptote. That's what this one's headed towards. If I try that trick out, though, over here with number 3, I'm going to end up with x squared over -1, which isn't going to head towards anything. As I put infinity in, this is going to spiral out towards infinity, which is not going to be a horizontal asymptote because it's going to keep going up and up and up and up. So our answer is going to be 1 and 2 only. So I liked it. It was an interesting choice. Again, not something that I would have expected, but it was cool because it did relate to when we did our limits, horizontal limits as we're going out to infinity. So that was pretty nice. I didn't see a lot of questions that dealt with these types of limits either. So that's why I put this one on here. Cool idea. Definitely something to remember in the future because it was a pretty tough question for us. Final question then. Oops, everyone got this one right. About limit notation. We did a good job translating the limit notation. The limit of a function of x as x approaches -11 is -2, and then that ends up being d. So that was pretty good. So everyone got that one as well, but I like that one. It was a good choice. Of the ones that I read that were of similar vein, I like this one. I like the different answer choices that they had, so that's why I picked this one instead of some of the other ones that were limit notation. So if you liked your limit notation question better, sorry, that's why I picked this one. I liked some of the different answer choices here. All right, and that's it. Because what just happened? So that's it. So that's all 31 questions. There we go. So overall, again, we did pretty good on the test. Just as a good reminder for AP Calculus, the AP scoring it's tough because it is a tough test. But again, it looked like most of us were headed towards a good score. Now on this one, if you were headed towards a 3 or 4 or a 5, that's really good because that's what you want to get on the actual AP test. We just have to be careful. We have to be cognizant that this is only multiple choice and non-calculator. So when it comes time to take the actual test, we're going to have to do the calculator section and all the free response sections as well. But getting a strong score on this non-calculator multiple choice is really good. We want to keep our skills up as we continue on throughout the year. I got a couple more topics that we're going to talk about in the class, but this is a really good base, and just being able to do all these is going to put us in a really good position going forward. So we did a really good job with that. So you should be pretty proud of what you did.